Welcome back. Today, we're diving into a really central question in artificial intelligence, the quest for control. I want you to imagine dropping a robot into a world it has never, ever seen before. There's no instruction manual, no map, nothing. So how does it go from knowing absolutely zero to mastering its environment and actually achieving its goals? That's the puzzle we're going to unpack today. So let's start with the big challenge. You've got this agent. It could be a robot or even just a piece of software. And you drop it into a totally unknown environment. There is no rule book. It doesn't know about physics. It doesn't know what's good or bad. It has to learn everything from complete scratch. So how on earth can it figure out the right thing to do? And believe me, this isn't science fiction. This is the absolute core problem behind some of the most exciting breakthroughs in AI right now. We're talking about everything from self-parking cars and autonomous robots to incredibly complex problems in biology, like protein folding, and even managing financial portfolios. Solving this is the key. Okay, so how do we even begin to tackle this? Well, in the field, we call it a model-free problem. And all that means is that the agent has no pre-built map of its world, no instruction manual. All it's got are its own actions and the feedback it gets from the world around it. So the only way for the agent to learn is to just try stuff. Seriously, it takes an action, it sees what happens, maybe it gets a reward, maybe it gets a punishment, and it uses that little piece of feedback to slowly, and I mean painstakingly, build an understanding of what works and what doesn't. Now here's where it gets really interesting. When it comes to this whole trial and error learning thing, there are two fundamentally different ways to go about it. Two different philosophies, you could say. Let's break them down. On one side, you've got what's called on-policy learning. You can think of this as learning on the job. The agent learns from the direct consequences of the actions its current strategy tells it to take. But then you've got off-policy learning. This is more like learning over someone's shoulder. Here, the agent can follow one strategy, say a really random exploratory one, while at the very same time it's learning about a totally different, maybe even perfect strategy. All right, let's dive into that first path, on-policy learning. This is the most intuitive approach, right? It's literally learning by doing, where an agent's strategy gets better based directly on its own real-world actions and their outcomes. The most basic way to do this is something called Monte Carlo control. Just imagine it's playing a full game of chess. The agent makes all its moves, plays the game all the way to the end, and only then, once it knows if it won or lost, does it look back and say, okay, which of those moves were good and which were bad? But right away we run into a huge problem. It's the classic exploration versus exploitation dilemma. If an agent finds a move that works okay early on, it might just stick with it forever. It's exploiting what it already knows, but it's completely stopped exploring to see if there's a much better strategy out there. Here's a super simple way to picture this. Imagine an agent is facing two doors. It opens the first one and gets a small reward, say +1 point. It opens the second door and gets 0. Now, a greedy agent, one that only ever does what it thinks is best, is just going to open that first door for all eternity. It'll never discover that maybe the second door actually leads to a massive jackpot later on. It gets stuck in a... And the solution to this is just beautifully simple. You just force the agent to be a little bit random. Most of the time, yeah, it does what it thinks is the best move. But every now and then, with a very small probability we call epsilon, it just picks a completely random action, just to see what happens. This tiny bit of randomness guarantees that it never stops exploring its world. Okay, but there's a problem. Monte Carlo is slow. I mean, waiting for an entire game to end before you can learn anything, that's super inefficient. A much smarter approach is to learn after every single step. This is called temporal difference, or TD learning. And when you put them side by side, the advantage of TD learning just pops right out. Because it's online, meaning it updates after every single move, it's way more efficient. It can even learn from tasks that don't have a clear ending, something Monte Carlo just can't handle. And this specific, on-policy, step-by-step learning method has a famous name, SARSA. The name itself is actually a handy little mnemonic for the 5 pieces of data it uses to learn at every single step. You've got the current state, the action it takes, the reward it gets, the new state it lands in, and, crucially, the next action it plans to take from there. It's a full little snapshot of its experience. Okay, so that's the whole learning by doing philosophy. But what if an agent could learn the perfect way to act even while it's just messing around and exploring randomly? Well, that's the incredible power of the other path, off-policy learning. It totally separates the act of learning from the act of, well, acting. And this is a total game changer. It means an agent can behave like a wild toddler, trying everything just to see what happens, exploring every corner of its world. And all the while, the student inside its brain is quietly learning the perfect, optimal strategy. It also means it could learn by watching a human expert or even reuse data from its own past, less skilled self to learn faster. It's incredibly efficient. And the undisputed champion, the algorithm that really unlocked the power of off-policy learning, is a famous one called Q-learning. So here is the absolute crucial difference. SARSA, remember, learns from the next action it actually takes. Q-learning is an optimist. It looks at the next state it landed in and asks, what's the absolute best maximum value move I could make from here, no matter what my current random policy says? It learns from the ideal path, not the one it actually walked. So let's put it all together. We have these two powerful approaches, these two main players, SARSA, our on-policy realist, and Q-learning, our off-policy idealist. Let's put them side by side and really nail down the difference. And here it is in a nutshell. SARSA is a realist. It learns the true value of the cautious, exploratory policy that it's actually following right now. Q-learning, on the other hand, is an idealist. It learns the value of the perfect, optimal way to behave, even while its body is stumbling around making mistakes. So here's your final toolkit for model-free control. We started with the simplest idea, Monte Carlo, which learns from whole episodes. It works, but it's slow. Then we leveled up to SARSA, the much more efficient on-policy agent that learns step by step. And finally, we got to Q-learning, the off-policy powerhouse that can learn the optimal way to win while acting completely differently. And this leaves us with a final and kind of mind-bending thought. If an AI can learn the perfect optimal strategy just by watching, even by watching our clumsy, imperfect experimental actions, it will eventually find strategies and solutions that we would never have thought of. Mastering an unknown world is one thing, but trying to understand the consequences of that mastery, well, that's the next great challenge.